I was not supposing, considering so much audience to be here for the RISC-V. Thank you again. Okay, let's let's start with our session. So I am currently going to speak on running Ubuntu on RISC-V. So most of us are familiar with Ubuntu, and right now on this UbuCon 2025 we have got many sessions going on RISC-V as well. So I think it's a hybrid topic that will cover both of them. So let's get started. So first of all, I would like to introduce the godfather of this plan, Mr. Nirjar Bulter, my co-author. Gladly, he is not here, so I got the opportunity to present. He is currently in Germany pursuing his fellowship, and he is associated with Yatri Motorcycles as engineer, and I am Sangam Ghimire, currently doing some engineering, breaking things, mending things at Spare SMS. So let's get going on. So before we start the topic, I would like to introduce about open source hardware. So most of us are very familiar with open source softwares. We use it for daily purpose. Ubuntu is itself an open source software. We go with the file system management tools that we go use daily. The programming language we use, most of them are open source software. But we might not be familiar with open source hardware. So today, first of all, let me introduce you all with what is open source hardware. What comes to your mind when we talk about open source hardware? A computer that is free to use for everyone? Maybe not. Or a library printer that is provided by the office or your institution for you to use? That's also not open source hardware. So while there has been movement for the open source, we have not been able to grasp much momentum in the open source hardware space. Currently, if we talk about open source hardware, what we can count on one, two, and the most primarily famous one is the RISC-V. So let's go to the core. What is or what are open source hardware? As the source code are shared in open source software, open source hardware shares its design. Like in case of the devices we use, the processors we use, the chips we use, generally we don't know how they are designed, manufactured. Many of us use earbuds today, but in most case we don't know how they are assembled, what's the protocol they are using, and if we want to reassemble it on our end, we can't go and procure the same hardware. We don't know about their specification, we don't know about their instruction set, and the proprietary hardware are generally so enclosed or so kept as a business secret that is very tough. There comes open source hardware. So general example of open source hardware that we deal most of the time are Arduino 3D printers. Open source 3D printers are now getting some momentums, and lab tools like OpenPCR, OpenBCI, LCR meters. And while we are talking on RISC-V, so it's an ISA, instruction set architecture. So OpenRISC, RISC-V, Leon are some general instruction set that are under the open source hardware. So what is an instruction set architecture? Just just now we have mentioned about the standard instruction set architecture and some example. So let's get going with what is instruction set architecture. Instruction set architecture, ISA, is the interface between hardware and software. Basically, we might know about system calls, kernels, and how the software interacts with the hardware. The bottommost level is designed or operated based on the ISA that it uses. Our ARM-based chips, our x86, x84 chips, every one of them has their own ISA, but they are not open. We don't know, or say we can't work upon them without binding legally or monetarily with them. There comes the use of open source hardware and open source instruction set architecture. It defines the instruction that CPU can execute. Most of we are familiar with these commands as we have worked with microprocessor, microcontroller, add, load, jump. We write program in the we write program for 8085, 8086 using these, And data types, ISA defines data types, integer, floats, vectors, registers, internal storage locations, addressing mode, how it's addressed. Generally there are 2-3 types of addressing mode we are familiar with, but we are not going to dive on this. And memory models, just like English has been a primary language for communication, ISA as the replacement for English when the communication happens between software and hardware. That's the language the processor understand, and in assembly language and guidebook for assemblers, that's the primarily used thing. Any question right now? So let's move ahead. So there are generally two types of ISA. One is CISC, one is RISC. The CISC one are already in your hands, the mobile phones, the laptops, and maybe that the camera we are shooting on, everything works on CISC. But RISC, it's on our stall right now. I think none of us primarily use this. So going on with RISC, it's a small optimized set of simple instruction for fast execution, efficient pipelining. It follows load store architecture. Generally we load and retrieve things from there. Uh, and it only dedicated load and instruction can access memory. I think we had a keynote session on secure computing as well. So this one objective matches with the secure computing model that we have as the keynote speaker for this conference. And in case of CISC, we are very familiar, so I won't give much insight on this. It's proprietary, and generally x86, x64 and legacy systems use them. Okay, now connecting the dots. So how is open standard ISA a part of open hardware? So as I have mentioned, if we want to design, say, the earbuds that XYZ company produce, we can't do it, as their hardware is proprietary, their instruction sets are proprietary, their software is proprietary, their design is proprietary, and even if we want to put in our design, our say our own hardware, we can't use their protocol. In one of the famous podcasts recently, Mark Zuckerberg from Meta has pointed out this, that the communication protocol that Apple uses to connect Apple with its ecosystem is open source, but it's proprietary. So they can't make it better or secure. So that type of problem are solved by such open hardware and open standard ISA initiative. It does not have no licensing fee, royalties are not required, and updates are driven by public demand, just like in case of Linux kernel. We can propose changes to ISA based on their defect and limitation. We can fork their existing architecture and redefine for our use case. We are going to see one of those example as well. And what's the actual need? So something most people don't even try out in their life is re-engineering what they use. We generally don't go in that way. Like the 3D printers we use, or the printers we use, we don't try to re-engineer or rebuild ourselves. But for people like us who are into making and breaking things, re-engineering becomes one of the core aspects for our career and for keeping our momentum going, our interest lively in the domain. So there comes the need of open standard ISA and open standard frameworks. Intel and ARM work just fine. I also use the ARM architecture device. But if I modify an ISA, I need to be either legally binded with them or need to pay some royalties, or in short, we just can't do it. Basically, we won't have enough information and we won't be able to do it. The legal challenges are kept aside. Sorry.
Like all this, what we are talking about is like changing the ISA if you want to.
Yeah.
But where would you change the ISA? Like what is you don't have. Yeah, you don't have any. So, we don't have any semiconductor facility to create our own devices, right?
Okay, we will be having a demo on that as well. We don't need, actually we don't need silicon.
Even if we think about FPGA,
Yeah.
like uh, if you think about a proprietariness of ARM,
Mm-hmm.
all the cores that we have, ARM Cortex A53 or
Yeah,
something
yeah.
like that, all the instruction set is open for us.
Yeah.
For a user to break and like get into the system, it's all open.
Yeah.
It's only closed. I mean,
For
it's not. It's only like you have to pay if you want to.
reproduce.
Yeah, if
or
you want to
say,
like make a profit out of it.
Yeah.
But if you think about it, if you want to make changes in the ISA, only you could use an FPGA, and FPGA is such a power-hungry device. You cannot basically make a product out of it.
No, that's not always true. We can have some workaround with that as well. FPGA is certainly power hungry device. I can assert on that. I am with you on that. But it's not always the case. Like reproducing is not only, or say for profit, that you have mentioned. When we go for profit, that's not only the case we get legally binded. If we are using it for our internal organizational process or say development, then also we get legally binded. No any such entity exists that monitors or helps us with such things. So in case of reproducing or for going for profit, it's an issue. But for professional internal use, you can work with it on your home. But proprietary, like consider I am an XYZ LLC and you are the ISA owner or say the legal authority, and if I am building internal projects and on top of that I am abstracting some other projects, then also I get legally binded with that. So that's one of the issue open hardware solves. Am I clear on this? Okay, thank you for your question. So let's continue. So the question, how do I implement it on hardware? Do I need to build my own CPU? Just now we were asked about the silicon chips and all. So this is one of the question we will be addressing. Can challenging an ISA really improve performance or efficiency that much? How would a proprietary ISA even create a risk to country security? So these are some questions we will be addressing under the need for an open standard ISA. So one fun questions. Why do you need to spend a lot just to watch reels on your phone?
Easier, simpler.
Our devices.
Full cost more.
Why does it cost more? Yes, that's all comes under this proprietary fee or legal binding that we pay for the architecture. ISA, the proprietary ISA that our devices uses, we have to pay royalty for them. That's why we have to pay so much just to watch reel. One of the fact that is currently another hot topic to be solved. So with Intel, it does not matter how skilled or ambitious you are, you simply can't legally build a CPU using their x86 ISA. It's completely locked down. As for ARM, even you are just trying to learn, you will meet with the paywall. There is a paywall to work around with that. The ISA documentation requires an academic access license that we were just discussing. The link we have provided over there. And our devices are costing more than it should be just because it uses a proprietary ISA architecture from ARM. Most of the mobile devices are nowadays powered using ARM architecture. So it's not just the number of instructions that matters. Now we are in the world, or say buzzy world of AI. The computation world is taking over everything. Every single one of us are in touch with AI, their products, in our daily day-to-day activities. So it's not always about the instruction set, numbers of instruction and all. It's about the data types that the ISA allows, and the flexibility with that. In ISA, if you handle basic integer, you are forced to emulate floating points vector. They are not supported by default in case of many ISA, but we will be showing a demo where we can work around with the RISC-V one. So when an ISA is rich, native data like SIMD vector, 64-bit floats, and even custom AI tensors can be integrated easily for massive workload in fewer cycle and less energy. One of the main pioneering point for RISC-V is less energy consumption. They are trying to achieve the goal, or say very closely in case of energy consumption with ARM chips. For right now, we consider ARM to be the most efficient, but RISC are moving very ahead, or say neck to neck with them as well. In short, well-designed data types don't just speed things up; they unlock the whole category of application that would be impossible otherwise. And going on with the proprietary vulnerabilities and the need for open hardware. Like if we are just to find out some top vulnerability attack in the proprietary RSAs, ISAs in the recent time, there are many. If you are even able to solve one of them, you are locked out due to their proprietary nature to contribute to them. So most of the time is no other option than waiting or getting upgrade from their side. So one of the issue that we can solve with open hardware or open ISAs is this. Every vulnerability found in proprietary ISA is essentially a 0 day because it's never solved from our side. There could be 1,000 more and we might be exploited but undisclosed. We are sailing a black sea at midnight without no stars, no moon, and with no idea what's beneath. I think so. What's RISC-V? RISC-V is a free open standard ISA based on RISC principle. So we have talked about RISC principles, right? Reduce instruction set, and it was developed at UC Berkeley in 2010 for education and research, and now maintained by an international organization or non-profit concept. Many of us are familiar with Linux Foundation, right? So generally, Linux Foundation collaborates with RISC-V and launch many mentorship program under the LFX Menti program. So if anyone is interested, you can go over there, watch it, contribute it. It's quite good. And then it supports 62, 32-bit, 64-bit, and experimental 128-bit architecture. We have taken RV64i for our reference in this case. We will be looking into it. It follows a modular design with small base ISA. If we have ever worked with modular software, then we know the benefit of this one. So a basic module is provided to us, and then we can keep on adding, appending, and upgrading on that. So similar pattern is followed by RISC-V. They provide a small base ISA, and then we can add extension for our need. So modular extension, let's go with this. So we have a table over here. Okay, this is not working, I think. Okay. So one of the extension is integer base. So it's basic for basic instruction. It's kind of mandatory because integer based calculation are primarily done every time. Then multiply and divide, and then atomic memory operations basically used for concurrency. Then single precision float, IEEE compliant for IEEE 754. Then double precision float for IEEE 754, and then compressed for 64 instruction to reduce the code size when we are building our code base. Then vector for scalable vector extension that will be heavily used for the current AI ML HPC workloads, and bitman manipulation for bit level operations. Then there are some for control and memory fence and custom extension that you can define. If you are working with 3D vectors or 3D tensors, that's not directly operated with proprietary ISA to the hardware, but in case of RISC-V, you can modify or adapt your applications based on the customized extension of the RISC-V, and that can improve the performance of your program by a huge margin. So one of the another feature we have is the privileged architecture. We do have worked with RBAC or least privilege principles in the software world, in the system administration world. If we are DBA, we work with it most of the time. But in case of ISA, we have these options in RISC-V. One is user mode, which is used for apps, user space process. Another is supervisor mode, that's used for operating system kernel. And we will be mapping this with the boot process in the Ubuntu on RISC-V as well. The machine code that's used, the machine mode that's used for bootloader, firmware, and trap handling, and the hypervisor mode that's used for virtualization and cloud platforms. So getting on with another feature, we have physical memory protection. So PMP is hardware feature in RISC-V used to control access to physical memory region based on privilege level. So we have just discussed about the privilege levels. Based on this, we can control the access to the memory region on the hardware. It uses a configuration register called PMP-CFG and address register that is PMP-ADR with it for delivering the control access to the physical memory regions. And each entry specify permissions like read, write, and execute that we commonly used in Ubuntu or any other Unix or POSIX based operating system. And it has address matching mode like TOR, NA4, and NAPOT, and lock status. And each address register holds the address or range boundary. So PMP has basically three modes that we have just mentioned: address matching mode, that is TOR, NA4 top of range, naturally aligned 4 byte, and naturally aligned power of 2. That helps us with maximizing the throughput from the disk level while accessing or performing read write operation. Generally, they are the most time consuming operation if we have fragmented data on our disks, and this helps us with that. And another is it can help us enforce the protection using supervisor and user mode regardless of the virtual memory permissions as well. So the last one is the lock bit in PMP can help us make it immutable until a system reset, preventing even machine mode from modifying it. So in the one of the keynote section, we were talked about encrypting the RAM. We were mentioned that the RAM pages can be assigned the ID for the process, and then that process can only access to it. So in that case, we are using the method of x86 and ARM, but in this case we can use this lock bit and this address matching mode to restrict the access over that as well. So this enables the security boot, trusted execution, and critical memory regions. I think we need to move forward. So what's about the trend? Trend is everything nowadays. It shows how it's being adopted. So if you look at the current status and the forecasted status published on January 2024, we see a huge growth and about $90 billion of market cap around 2030. So it's quite a good domain to make your career as well. And what about the current status? I think we many of us use FreeBSD, OpenSUSE, SSH, TLS, Redis, Nginx, MySQL, and many more. The safe one is used for HPC, and everything is supported over there. The Rust is supported, Go is supported, Python is supported, so it's quite good. The OpenCV is supported. And again, talking about my domain infrastructure, we have Docker, Go, Jenkins, Maven, everything aligning with the RISC-V. Everyone is getting on the track to support the RISC-V architecture. And now finally to our core topic. So starting with the first Linux kernel with RISC-V support, it was 4.15 released back in 2018, and then the first Ubuntu release after the kernel support was there, we got it around 2020, and official canonical support has been there since the first release, and they are primarily targeting boards like those from Sci-Fi and similar platforms. UEMU for simulating our workflow, and then we are getting some utils over there, and then we have Docker compose file where we have some configurations. We are giving it name, we are building the same image, we are giving it access to whatever it needs. We have provided the installed simulator over here, then machine, and dot. Everything is not required here. So one thing we can note over here is we are providing it the 64-bit RV, we have mentioned that we have RV32, RV64, and this one is the current one we are working on, and it's mapped to the okay, we are booting things. So one thing we can note over here is we can see the instruction call. Every instruction call, every syscall made over the booting process is visible in our architecture. It's not quite the same when we use the other one. We can't see every system call or process call being done, but it's quite visible here. So we will go with this one as well. What's OpenSBI that we are using? We have this, but for now, and then let's wait for some time. Mhm. Okay, I think we are finally. It's still taking some time, so let's wait. Okay. Okay. Let's log into this. We have already mounted our keys over there, so we can SSH into it without any problem. So we are into this now. LS. So for now we have over here is one RVV demo. So RVV is the RISC vector data type, RISC-V vector, and why I have choose this one is we are generally performing AI ML workload and AI ML related tasks, or say high computation tasks in the vector data type, and vector data types are not natively supported by other instruction set architecture. So we will be running over this one. So let me show you what we have. Demo.c. Oh, sorry. Mm-hmm. Oh, sorry. So we are just trying to show how we can customize and build for the based on our instruction set architecture. We will be building this program based on the scalar and vector both, and we will be comparing the performance, how the vector one we are providing based on the custom ISA extension can help us one script as RVV underscore demo that builds it on both scalar and vector one. So let's build it and see. I think it should work. If not, then I'm going home. No, no time soon. We are inside the simulator, so it's quite comparatively slow than building on native system. Let's wait for some time. Oh, okay, while it's keep on working here, we can go back to our slide. So we have gone through the booting process already, and we will now talk about the booting sequence. So what happens in our common flow is we get it from ROM to our loader, then runtime, then bootloader, and then OS. But what happens, what we just did was we had two different modes. We have talked about the privileged mode in the previous slides. So the first three steps go in the M mode, and then we go to the S mode. So zero stage bootloader is the first small piece of code that's stored in on chip ROM that runs first. Then we have the first stage bootloader, and it's responsible for passing control to the next stage. Then we have OpenSVI, the one we have seen in the first phase running the container, and then we have Uboot, and then we have the loading of the OS, the final stage. So we have a different boot flow, entirely different boot flow in the RISC-V architecture and the old one. So let's just go through the stages we have discussed. It after the system reset, it's the first code that runs. It reads the modal select pins to determine boot source such as SD card, SPI flash, UART, and proceeds, and its role is minimal but critical. Let's go to the second one. Here it works with the L2 cache or on chip SRAM. The first stage bootloader works on that. It is responsible for initializing the DDR memory. It sets up clock, peripheral interfaces, device trees, and boot parameters. And then the main job is to load the full bootloader. The one we have just seen over here. Its main job is to load the full bootloader. And then supervisor binary interface, the SBI we have just discussed. It's standard interface between OS in S mode and firmware in M mode. So this is not the common flow that we see in the our day-to-day device that we use. And then it's responsible for providing access to machine level services like timer, interrupts, and other shutdowns. It's a fancy abstraction between binary and system call. And then we have this pretty little image and the URL. This one is quite good. It's a presentation from 2024 by the team of OpenSVI. We have it over there. You can visit it anytime. We have just discussed how this is done. And what's OpenSVI? It's an open source project maintained on RISC-V Foundation, making RISC-V platform. It's OS friendly and easier to port across different board. So that's another aspect of the open hardware initiative we were talking about. Its goal is to provide a reference implementation of the RISC-V supervisor binary interface for platform specific firmware running in machine mode. So we have the three options to build the OpenSVI, and they are FW payload, FW jump, FW dynamic. So they have their own feature. I think we are short on time, so I'm skipping it. If someone is interested, it's based from the same presentation of the team. And then Uboot. Universal bootloader is a flexible bootloader that initializes the hardware and loads operating system like Linux and embedded system, including RISC-V. It's compatible, it's friendly to use, and it runs after the FSBL and OpenSPI load once that loads into the Linux kernel. And Uboot supports boot script, environment variable, multiple boot source. I'm not sure if our current bootloader supports environment variables or not. I'm not familiar with that, but this one supports it, and it's widely adopted across different architecture like ARM, x86, and RISC-V. And the OS was the last step. We are already familiar, and one point we can mention is the OS runs in S mode, meaning it cannot directly access the hardware. So it provides a layer of security and abstraction as well. And RISC-V was supposed to change thing. I have been blabbering about all about RISC-V, why it's needed, why it's best. But how are things going on the ground? Has it changed? Has it make some real impact? Has it been able to solve some real problem? So we are going to go through the performance and power evaluation for now. On the data processing and experimental R&D domain, boot time evaluation, performance evaluation, and power consumption evaluation. So here is a table. x86 is still on peak when compared to the CPU performance. ARM is near parity, and RISC-V is rapidly improving. We are talking about the RV64, 64-bit one. And for performance per watt, x86 is not the leader. We know ARM is the leader in the energy efficiency domain, and RISC-V is better when it's tailored, like the demo we are going to see soon. And regarding the boot time, we also lag there. And the CPU, Sysbench CPU, the Sysbench, we have been using Sysbench for benchmarking in systems domain. So There also we are lagging from the x86. The OpenSSL and SHA-2256 cryptography algorithm, we are lagging there. AES we are also lagging, and 4K rendered KIOps also we are lagging. Then why are we talking about this? So this table is based on the algorithm that's generalized for x86 and ARM. We have not yet performed or say modified the algorithm so that it takes the advantage that our open ISA provides, like the one we were talked about using vectors and all. So if we compare someone else choose with us, we are always going to be last in the race. That's why this table does not tell us the entire picture. So what's the finding? We have just told, and again to note, we are talking about the algorithm that is generally designed for the x86 and ARM. Yes. Then where are we talking about it? It's the only mainstream ISA you can legally customize, and if we are able to tailor the workload that we are going to see, then its performance goes to around 50, 60 to 100% better as compared to the existing architectures. Standard extensions like vector, bit manipulation, and the one we talked about, the crypto hypervisor, are few custom operation codes for hot loop, and the magic boom. It beats nearly every other system each time if we are able to customize it to take the advantage. Ubuntu, GCC, OpenSSL, Tensor libraries all have RISC-V paths. You can ship software today and evolve the silicon tomorrow. That's what I was asking about. We don't need to manufacture the chip today. We can currently modify the software and maybe make the silicon wafers later on. Okay, the hot topic. What's its use case in the current AI world? So RISC-V has been widely adopted basically for four things. One is IoT device. It requires less power. We can customize it. IoT workload are very memory should be very memory efficient. They are generally provided with low computational and space storage. So making things over the RISC-V helps us with that. Autonomous vehicles. If we are interested, we can explore how the Chinese EV industry has been using RISC-V for their autonomous and electric vehicle. So it's quite an interesting case over there. The edge server that needs to work fast, sort the cache data fast. They are also working on the RISC development of RISC server and solving the use case over there, and the mobile devices to make the cost cheaper. Right now also we have framework or open frame, deep computing. They are solving the customizable laptops, I guess, over there. So we have such initiative in the mobile device domain as well. So besides this, in the AI domain, we are seeing high use of RISC-V on inference. Uh, Currently, NVIDIA is the market leader, obvious, in the both training and inference device for the AI. But they are also adopting this RISC architecture over their uh, toolcase and the VLLMs, softwares, inference softwares. They are making everything from hardware to software level. They are making everything compatible so that inference can happen on the edge device. Your mobile should be able to solve as an inference machine for your use case. Personalized AI, to be precise, and the accelerated machine learning model like RVV, RISC-V vector extension, and faster matrix multiplication, because matrix multiplication is the backbone of ML, and bit manipulation and custom AI accelerator. So before the takeaway, let's go back to the build. Oh, successful. Okay, then what we did was we. Oh no. Yes. So we did a scalar build, we did a vector build. If we can see the same for the microsecond here, we can see. Look, the scalar one takes about 281 microsecond, and the vectorized takes 235, and same over here, it's takes 584 microsecond, and vectorized takes 342. So it's quite good progress in this simulated environment. We are not working even now with the native hardware. So if we get to work with those hardware, it's quite better. The second one, it's around 90% gain, I think. it's twice better, 342 to 584. Then we have a comparison script as well. We can see what's inside. Compare ISA. Okay, let's see what's there. So if we see, we have the report over there, the RV64 that we mentioned, the vector one we have been using, that's the core factor that improved our performance, and we have it over there. But in case of scalar binary build, we don't have it, so it lacks in the performance. And if we can see over here, we have another data lower is better for the vectorized and scalar comparison. So it's quite obvious that even if we can take the advantage of our small computational tasks and if small software development with the customizable extension provided by RISC, we can surely save some cost on the computation side. And then what's the takeaway from the today's session? Maybe for raw and general purpose, throughput and crypto x86 leads for now, but if we can customize, we are obviously the winner. ARM matches much of that at far better efficiency. We are talking about the energy efficiency. RISC-V is already viable for embedded and edge devices, edge server, and catching up fast with custom extension, the RVV one we just talked about, and domain specific accelerators. So thank you for your patience. Any queries? Please go ahead. Yes, sure.
Yeah, I heard that Google and some AI companies are creating their own CPUs to train their AIs and run their AIs. Do you know if they are using RISC-V or something else?
What happens in open hardware is, if we publish the ISA and all, it's not compulsory that they will exactly follow the same. They can have their own internal hardware design and they can modify the existing ISA as per their need. So for me to claim that they're exactly using this is not viable, but they are opting for the open ISA and open hardware, that's for sure.
So I had one doubt. Like right now, even if I buy a RISC-V phone, like maybe a Pine phone, right? Pine phone, I think has a RISC-V processor in it.
As far as I know, yes.
So the price will still be the same, right? I mean, for the performance per buck, if I get a Mi phone maybe which is worth like 18,000, 20,000, something like that, I get a Pine phone even more expensive. Like it'll cost me like 30, 40, right?
Yeah.
So like my question is, I really think like RISC-V is only gonna be beneficial for big companies who are like going away from ARM and like all those x86 processors. They really want to sustain and build and sustain their own servers. They don't want any dependency on anyone else. That's where I see RISC-V, to be honest. What are your opinions?
Regarding the price, one of the factor that drives price is if we add even 100 GB of storage in our, say, Apple M2 to M3 upgrade, then it costs us around $300. But in real market, the storage is not that expensive. So there is business. Pine may be having some consultant from McKinsey or somewhere who are giving them such ideas, because generally stories are cheap, and in real world it's not how things work. If even though they are cheap, the company may produce it or may pitch it as a unique product, they can have high value, but I can't justify the high pricing of Pine as well. So basically what I believe is, if everything is open source and everything can be modified, developed, then the price should go down. We should ask the Pine why they are increasing the price, or say pitching their prices over at that scale. But that's the business aspect of the things. Am I clear for that? Thank you. Any more questions? No? Okay, thank you everyone.